On behalf of the College of Natural and Agricultural Sciences at UCR, welcome to the fifth presentation in the 2014 Science Lecture Series. And as usual, I'm very happy to especially welcome some of the schools that are here, Norco College, Riverside STEM Academy, RCC at Moreno Valley, and Murrieta Valley High School. So great that you guys in particular came tonight, and as always, keep UCR in mind for your future education. I'm Mary Drosser. I'm a professor of earth sciences here. And before I get started, I just want to ask each of you to fill out the questionnaire that I think you were handed as you came in. It's with your program anyway, and it helps us identify our audience to make sure we're sort of communicating with you guys in the best possible way. So that would be great. So after the end of the lecture, you can give your questionnaire to one of the ushers or place it. I guess there are boxes at the two exits, so that would be great. Thanks. I'd also like to thank the sponsors of this year's science lectures. As they have been for the last 5 years, the lectures are supported by the College of Natural and Agricultural Sciences. Support this year has also come from the Department of Earth Sciences, the Office of Research and Economic Development, and from the new Environmental Dynamics and Geoecology Institute, or EDGE. This is a new institute at UCR, and many of you who probably have this memorized now because you've been coming to so many of these, which we appreciate. The institute is unique in that it brings together scientists from earth sciences, biology, chemistry, physics, and environmental sciences to examine the issue of life in this changing environment. And the person who will be director of this institute will hold the W. Mayhew Chair in Geoecology, which has been made possible by a $1.5 million gift from donors who wish to remain anonymous but who are passionate about the ecology of the Southwest. And we are deeply grateful to these donors, especially for commemoration of Bill Mayhew. Dr. Mayhew is one of the founding faculty members at UCR and was one of 3 individuals who established the University of California Natural Reserves. So these are exciting times for geoecology at UCR, and I'm especially excited to introduce Scott Wing as our 5th speaker in this lecture series. Dr. Wing is curator of fossil plants in the Department of Paleobiology at the Smithsonian, the Natural Museum of Natural History. This is obviously, as many of you know, located in the Mall in Washington, D.C. And Scott is a biologist, but instead of studying living things, he studies fossil plants with the goal of understanding evolution, ecology, and environmental change. And one of the things I would say about Scott is he was one of the first people to really use fossil plants in looking at past climate change, and sort of his name is synonymous with the use of paleobotany of fossil plants and understanding climates of the past, which is important as we look to understanding our future climate. In tonight's talk, he will be focusing on what we call the Pale-Eocene thermal maximum. This change took place 56 million years ago, but it's important as we look to what might be happening in our future. So tonight we're going to hear about, from Scott, things we can learn about events that happened a long time ago. So, Scott.
Thank you very much, Mary. It's a pleasure to be here, an honor to be here, and your words are too kind. I need to teach you more about the history of paleobotany. They're actually, I wish I were a founder of using fossil plants to look at climate, but it's been done by people who are even older than I am. So, but what I do want to do tonight is to try to give you a kind of geologist's eye view of the future, which may seem a little counterintuitive. But what I'm going to do is start off by explaining to you why I think the event that I'm going to talk about tonight is important, sort of frame it that way, and then get you a little bit into the details of what happened 56 million years ago during this major global warming incident, and then come back at the end of it, sort of return to the present and look a little bit at the future and try to think about what a geologist's eye view of the future how that might benefit us. I hope it will benefit us. So let's get started. This is something that I'm sure a type of graph that you've probably seen before if you're reading the newspaper or paying attention to science in almost any venue. It's just a graph of the amount of CO2 in the atmosphere from 1880 to almost the present. And you can see that it's climbing quite noticeably, and probably everybody knows that this increasing amount of CO2 is the result of human activities. And you can also see the temperature here shown as deviations from global average temperature, and you can see that these red lines here indicate that temperature has been rising quite rapidly in the last several decades. So if you're a paleontologist or a geologist and you look at a graph like this, probably the first thing that you wonder, I know there are other geologists in the room, we all think the same way. They say, well, if you added a little more onto that record, you might know more. I want a longer time sequence, longer time series. But before we go into the past, I want to also think a little bit about the future. And these are projections mostly. They start in the present here at 2014, and then they go out several hundred years into the future. And these are projections from the latest Intergovernmental Panel on Climate Change assessment, the 5th assessment report that came out last fall. And there are a series of representative concentration paths, as they call them, for greenhouse gases that are shown here in red lines. And of course, nobody knows what the concentration of greenhouse gases is going to be in our atmosphere in a decade, or in 2 decades, or in 3 decades, much less in a few centuries. But they have to make some guesses based on possible scenarios for economic activity and carbon efficiency of the economy and things like that. So these are projections that show different ideas about different scenarios basically for how the carbon dioxide concentration of the atmosphere might change going out. And these are projected surface temperatures that correspond color by color with those carbon dioxide concentrations. So you can see that even though we are at about 400 parts per million of CO2 now, that in a relatively business as usual economy without increasing efficiency, we could end up easily over 1,000 parts per million in about 2100 and continue to rise after that. And even with much more kind of conservative assumptions about how much CO2 we're going to produce, we could still end up with well over 500 parts per million of CO2 in the atmosphere. So we are not just in a period of time where things have changed rapidly in the last 4 or 5 decades, but we are in a period of time where it seems extremely likely that they're going to change even more in the decades ahead or in the centuries ahead. So we're like those people who get to live in interesting times. This is an interesting time to be alive in if you're thinking about the climate. Let me actually see if I can do a little trick here. I'm going to try to get out of this and into a movie, because I want to show you a movie of how CO2 has changed over the last few decades. This is a movie made of data by people at NOAA. And what you're seeing here is an animation. I'll go to this screen. And this blue point here is at South Pole Station. That's the CO2 level starting in 1979. You have a clock here in the middle that's ticking off the years. The red dot here is the Mauna Loa Observatory in Hawaii, where also CO2 has been measured for a long time. And then there's stations that are in various places in the ocean on buoys or on land, and you'll see that those start. But what you're seeing here is basically describing this graph with these seasonal cycles here. So notice that the South Pole station is just kind of climbing steadily, the blue dot, but the Mauna Loa station is going up and down. And the reason it goes up and down is that when it's spring in the northern hemisphere, actually we caught it in the wrong time of year. I'll try to catch that just at the right time. Okay, so CO2 goes down because there's a lot more land in the northern hemisphere and there's a lot more vegetation in the northern hemisphere. When that vegetation comes alive in the spring, it pulls CO2 out of the atmosphere. So what you're seeing in the graph here is the seasonal cycle that has to do with photosynthetic activity in the northern hemisphere. Start that up again. We're now at 1998. You'll see that a lot of the smaller open circles that are in the northern hemisphere have an extremely variable pattern of change. And that's because some of those are on land. So you're seeing CO2 pulses that come from cities or industries or traffic or whatever. And some of those are going much higher. This graph will continue to climb its way. And some of you may be aware that last spring, CO2 at Mauna Loa briefly hit 400 parts per million of CO2, which is very substantially above the background. And you're seeing this graph now. So now what we're going to do is we're going to add historical data going back in time. See if I can get that out of the way. And this is the famous Keeling curve data from starting in 1959. You can still see the seasonal cycle. But then we're going to add shallow ice core data. So now we're going back through historical time, back here to about 1,000, and look at the rise in CO2 here. That's what we've been busy doing. Now we're going to go back even farther with more ice core data. So these are relatively recent ice core data back to about the year 0. And now we're going to add deep ice core data going back farther and farther, 10,000 years, 15,000 years. So now we're getting back to the last glacial maximum, a time of colder climate, and lower levels of CO2 below 200 parts per million. And then you'll start to see the seesaw. And now the seesaw, instead of being seasonal, this is the glacial interglacial cycle. So these are cycles that are tens of thousands of years long. And now we're back into the very oldest ice on Earth, looking at data from Antarctica. So that's the Vostok ice core. So that's beginning to be the way a geologist looks at CO2. And the problem with this is that, at least the problem for me, now we're going to get the advertisements. They didn't show the previews of the next movie here. This is the problem with this is that, in spite of being a very long record, and actually I've got another. Go back to the PowerPoint. So in spite of being a very long record, and here's that record again, it doesn't have anything like the future. It doesn't even really have anything like the present in it. So again, simple-minded geologist, you see a long record like this and you think, well, there's not really any precedent for the future or even the present in the last 800,000 years of atmospheric history on this planet. And not being smart enough to think of anything really clever to do, you just want to add more record onto the back of that. And there's actually not any ice on this planet that's old enough to record more time than 800,000 years. So the record gets sloppier in some ways, but you can make an effort to do this. And many people have. There are lots of different geological proxies for how much CO2 was in the atmosphere. I don't have time to go into those, but the lines that you can see on this graph, I'm afraid the pointer has given out. The lines you can see here are showing you pre-industrial concentration of CO2 there at about 280 parts per million. Where are we now in 2014 is the orange line. And where we expect to be, and that's the whole range of IPCC estimates for the amount of CO2 in the atmosphere at the end of this century, 2100. And you can see that in order to get to 2100 levels, you need to go back something like 30 million years. And in fact, even to get to 2014 levels, the levels we're at now, you might need to go back. There are a few high points in there at about 5 million or 3 to 5 million, another about 20 million. But basically, the amount of CO2 that's in the atmosphere now, it's increased. Oh, thanks very much. It's increased. This is going to test my ability to use two instruments at the same time, because one of these is the clicker and one's the pointer, and there's not any telling which one I'm going to use for which. Oh, that's great. That's a pointer. You all behave. Yeah, basically, CO2, since I was born, CO2 was down around here when I was born. It was sort of almost it was in the range of recent Earth history, and now it's not anymore. And those of you who make it to 2100 will find that you really would have to go back to the Eocene to find a time with CO2 levels that high. So this gives the past a new relevance that it's never really had before. When I started off in paleontology, I had absolutely no thought that it would ever be useful in any way whatsoever. And I sort of feel like relevance arrived sometime in the last few decades. So what about temperature? Those are our very imprecise estimates of CO2. Oh, and you should notice, I meant to point this out, that this scale is actually kind of getting scrunched together as you go up. So you notice that the tick marks are marking more amounts of CO2 as you go up. What about temperature? This is temperature in the last 65 million years, mostly as estimated from the chemistry of the little shells of tiny planktic marine organisms that have been cored out of the bottom of the ocean. Here we are in 2014. Here's the spread for 2100 from the IPCC projections. And it looks as if we are also headed to temperatures that have not been around for a very long time. And I want to particularly call your attention to this period back here, because that's what we're going to be talking about, when Earth climate was really quite warm, a lot warmer than it is today. And actually even warmer than it probably will be in 2100, although that remains to be seen. So it was a planet that in many ways is not that different from today's planet. So 50, 60 million years ago, but many of the continents are in similar positions. So if you may be thinking in the next minute or two, gosh, that must be because continents move around. Well, continents do move around. Australia is a little suspiciously far south here. India hasn't collided with Asia yet. But North America, South America, Africa, they're in recognizable positions. So this is not an alien world that looks utterly different from what we're used to, but it is an alien world as far as its climate is concerned. These big black things here are tree stumps of dawn redwood, and this is Axel Heiberg Island in Canada at about 80 degrees north latitude. And that is the modern vegetation at that latitude. This forest is actually very well characterized. You can look at the stump diameters, you can look at the growth ring size, and the productivity of this forest is estimated to have been something like the productivity of coniferous rainforest at the latitude of modern-day Vancouver. So, but it's growing here at 80 degrees north latitude 50 million years ago. So characteristic of this really warm climate is that the poles are even warmer than we think they are. The whole Earth was warmer, but the poles were really warmer. And this kind of dramatizes that. This gentleman here holding a photograph in the modern-day Canadian Arctic, holding a photograph of Okefenokee Swamp in South Georgia, which is probably more like what the Canadian Arctic was in, say, 50 or 60 million years ago. Another characteristic of that warm climate period is that winters were warm even in the middles of mid-latitude and high-latitude continents. So this is a palm frond from Wyoming. Nobody here would be surprised by a palm tree, but people in Wyoming are very surprised by palm trees because it's too cold there in the winter for those. And this is a symbol, symbolic in the same way as that previous photo, except that I got to be the model for this one. I've worked in the summer in Wyoming. I've done field work in the summer in Wyoming for probably, well, more than 40 years now. And I almost never go there in the winter, but the guy who took this photograph persuaded me that I needed to go there in the winter to have this photograph taken. And I swore I would never go back in the winter again because it was a beautiful sunny day. It was about 20 degrees, and as soon as the sun went down behind the mountains, which it did about a minute after this photograph was taken, the temperature dropped to about minus 20, and I stopped smiling. So, but there were alligators living there 50 million years ago, 55 million years ago, 60 million years ago. There were big reptiles related to alligators living in the same area. So again, it was a continental interior where it didn't chill in the winter nearly as much as it does today. So we're talking about a period that we don't fully understand. We have this enigmatic warm climate, but I'm going to focus for the next little bit on a blip, the riddle wrapped in the enigma of this warm climate that lasted for tens of millions of years, and that's this Paleocene-Eocene thermal maximum. And it's so short that it looks like just a line here, but in the next slide I'm going to blow that up. So notice here we've got millions of years, tens of millions of years on each tick mark. In the next slide, well, we either missed a slide. We missed a slide. There's a slide missing. Oh well. You would have seen that actually if you expand that outward, you see a shift in temperature that lasts about something like 20,000 years, perhaps shorter than that, where temperature increases by about 6 degrees Celsius. And at the same time, there's a change in carbon isotopes. So many of you might know that there are two stable isotopes of carbon, carbon-12 and carbon-13. And just as the temperature is increasing, there's also a shift towards more carbon-12, less carbon-13. And that shift is seen globally. At the same time that those events are going on, you also, if you're taking cores of the deep sea, which is what these are, you see a sudden shift in the sedimentation. So the way you read this core is the end that's towards you is the young end, and this would fit onto the bottom there. So these are just sections of core that have been drilled out of the bottom of the ocean. And so you're coming up through the very end of the Paleocene here, and then you get to this point, and that's the onset of the Paleocene-Eocene thermal maximum, and suddenly the sediment goes red instead of being white. And the reason it's white here is because it's chalk. So this is sediment that's made of the bodies of the shells made by tiny marine plankton, mostly coccoliths, things, little algae that make a calcareous shell, and they die, fall to the bottom, and most of the sediment in this area and in many areas is composed of their shells. Here, it's not white anymore, it's red. And the reason is because there's much more iron in the sediment. And the reason there's more iron in the sediment is because these little tiny limestone shells have been dissolved away. So right at the same time as we have the increase in temperature, a very substantial increase in temperature, and this change in the chemistry of carbon, we also dissolve away chalk in the deep ocean. Oh, here's the slide I was looking for. And you can see it's just the way I said it was. There's this red line here, which is temperature as inferred from the chemistry of oxygen in those little shells, and the white line, which shows this shift in the carbon isotope ratio. And the whole event lasts about 200,000 years, but the onset is less than 20,000 years. Well, we can put that information together, and what we come up with is that this event represents global warming of about 7 to 14 degrees Fahrenheit, that's 4 to 8 degrees Celsius, dissolution of deep ocean chalk, this change in carbon isotope ratio shifts about 5 parts per thousand, which is a very large change, and the event lasts about 200,000 years. And you can put those together, and you can think about them in terms of how carbon moves through the atmosphere and the ocean, and the conclusion is that we're looking at the release of something like 4,000 to 7,000 billion tons of carbon, which is the size of the current fossil fuel reservoir. Now, the past starts to get even more interesting. It's like, this is not only is this a warm time, but this is a time with a very rapid release of carbon, and it's about the same magnitude as what would happen if we burn all the fossil fuels that we have today on the planet. So you might be wondering, where does the carbon come from? And the answer succinctly is we don't know yet, which is kind of embarrassing because this is something that people have been working on this problem for almost 25 years, between 20 and 25 years. And the first question that anybody asked was, where did the carbon come from? And we're still trying to solve that one. But it's beginning to look as if part of the answer comes from methane hydrate deposits in the ocean floor. So microbes that eat up organic matter that falls to the bottom of the ocean, some of them release methane as a byproduct of their metabolism, and because it's the bottom of the ocean, it's relatively cold and it's very high pressure. That methane doesn't come up, it actually gets trapped in ice-like compounds in the bottom of the ocean, in the sediment at the bottom of the ocean. And today, we still have these today. They actually burn if you can light the ice on fire. It's quite dramatic. So that's actually a leading contender for where the carbon comes from, but it also is beginning to look as if there are multiple sources involved. So another possibility is wildfires. Another is heating up organic matter by volcanism. This is when the North Atlantic was rifting open very actively between Greenland and Scandinavia. And it's also possible that permafrost on Antarctica, which is probably the only place on Earth that would have been cold enough to have permafrost, it's possible that permafrost was involved as well. But again, we're still working on this. So the Paleocene-Eocene thermal maximum is now known from a lot of places around the planet. These white dots are all cores taken from the deep sea. There are also a few places where we know it on land, and those are the red stars. And what I'm going to do is take you to the place I've been working for a long time, which is here in northern Wyoming. It's a place called the Bighorn Basin. And those mountains around it were rising during the time that the Paleocene-Eocene thermal maximum was happening, and actually before and after as well. And this shows you badlands near the bottom of the Bighorn Basin that are being eroded today, but these were deposited by streams that were coming out of the Bighorn Mountains, which are snow-capped in here, behind you, off to the east. And so rivers would come out of these mountains and dump sediment in the bottom of the basin, and year after year after year, more sediment accumulated there. And these red stripes are places where soils formed, and iron was oxidized in those soils, and that's why you're getting the red stripes. So this creates a place where conveniently enough, 56 million years ago, there was a lot of sediment being deposited, trapping a lot of fossils, and giving us a place that is now being eroded, where we can go study fossils and what happened during this time period. So as I said, I've been working there most of my life and spending a huge amount of time doing something that occasionally seems pointless, but also is occasionally very rewarding. It's a lot like, probably a lot like gambling, I suspect. I don't seem to have any interest in gambling, but collecting fossils I have a lot of interest in, and you're just always willing to give it a try, even if you think the probability of success is very low. So I go out and plant fossils, unlike vertebrate fossils, some of you may be familiar with those, they often weather out of hillsides, but plant fossils don't usually weather out. They're in there, and the only way to find out if they're there is to take a shovel and start to dig them up. But of course you don't know if there's anything there. So you spend a lot of time with a shovel wandering around, digging tiny little holes to see if anything comes out. And sometimes something does, and then you dig a little bit bigger hole, and sometimes there's pretty good fossils in there, and then you get your friends and you dig a bigger hole, and sometimes they're really good fossils. And then you dig a really big hole, and this is my favorite hole in the ground, because partly you can see this on Google Earth. That's one reason it's my favorite. And the other reason it's my favorite is because this is the first site where I got really good plant fossils from the Paleocene-Eocene thermal maximum, this 200,000 year period when the climate got really warm. And the day I found this place, I was with a student who had never been in the field before. And it was maybe the second day of the field season. And it was I think it was about 4 o'clock in the afternoon. It was really hot, as it often is. And we had gone pretty far away from the car, and he had run out of water, and we hadn't eaten lunch, and we were a long way from the car, so I thought we just should keep checking to see if we would find anything. And I went over a hill and found and was digging away, and he was sort of standing there wondering what he should do, and these fossils started coming out, and as soon as I saw the first one, I realized that these were different from all the fossils I'd seen in this area before, so it had to be this special time that I had been trying to study but hadn't found any fossils from. And I was kneeling on the ground, digging with the shovel and looking at these things and exclaiming how wonderful they were and getting very excited. And then I started to laugh because it just seemed so ridiculous that finally here it was. And then I started to cry because I was so happy. And so there I was, on my knees on the ground, sort of chopping at the hillside frantically and laughing and crying. And then I remembered that I had somebody with me, and he didn't know why I was laughing and crying, and probably what he was thinking was that he was going to die in the desert without any water or food. So I said, you have to understand, I've been looking for this since you were 8 years old, and it's finally here it is. So he made it back safely, but he never came back. So anyway, that's my favorite hole in the ground. Once we find beautiful, these are some of the kinds of leaves we find in that particular place. We wrap them up in really high-tech wrapping gear from janitorial supply companies, and take them back to the Smithsonian where I study them and try to figure out what they are. And over a long period of time, I've put together a pretty large number of sites across this Bighorn Basin area, and this is just a way of displaying the sites, and you can see marked off here in tenths of millions of years, and then each one of these X marks is just a place where I've collected plant fossils and it's positioned on this axis by how old it is, and then I just just basically piled them up, and here's the PETM. So you can see I've got some sites now, maybe 20 or so sites from the PETM, and a bunch more, maybe 40 from before, in the last couple of 100,000 years before, and a bunch after, and then there are also more. If you expand the time frame, there would be more than this. And what I've done is I've used those collections to put together ranges in time for each of the species. So you go to a site, you collect, you say who's here, you make a list of who's there, and then you go to the next site and you make a list there. And eventually it allows you to put together a diagram like this. So once again, here's the PETM. And each of these little horizontal bars just represents the range of a species in time. So it starts, sometime back before this diagram starts, and these species come up to here, and then they're gone. There are other species that start somewhere during this time interval and keep going through the end of it. And you can divide these ranges up into some different categories, if you will. And these species would be species that you'd say, well, these might have gone extinct sometime near the beginning of this PETM event, because they come up pretty close to the end of the Paleocene, and then we don't ever see them again. And these guys they're only found in the PETM. I've never found them before, and I've never found them after in decades of looking. So that's kind of strange. They're only there during the event, during this very warm time. There are some that go right through. They don't seem to care that the PETM happened. And then there are others that come in right as the event is ending or just after the event is over, and they keep going into much younger times. And then the strangest group are these guys these species they seem to be around in this area. They're around before and they're around after, but I've never found them during the PETM. So that seems quite peculiar. So we have possible extinctions, these kind of unique PETM plants, some that are Eocene, they're characteristic of the Eocene, the time that came after, and then we have some that are candidates to have just been locally extirpated, so that they didn't go globally extinct because then they wouldn't come back again, but they appear not to have lived in this region during the PETM. And these are color-coded, and I'm just going to show you a few pretty pictures of plant fossils, but also maybe give you a sense of the kinds of plants these are. So the blue here, possible extinctions, these are both in the big group that includes dogwoods and other plants that today grow in relatively seasonal, although tend to be on the mild side climates. So that's where their living relatives are. Many of the common species that are found only during the PETM belong to the bean family. And that's something that would be common if you went out into the desert in Southern California or even farther south in Mexico or Central America. Some of these are related specifically to plants that today occupy dry forests from, say, Mexico down to Paraguay. Interesting that they're only in Wyoming during this event. Then, I went the wrong way there. Then the ones that show up after the PETM is over, these are the ones that appear in the Eocene. And again, there's sort of generally a temperate feel to these guys. They're things related to linden trees, alders. This is a hickory family. This is a kind of fern that grows in the temperate zone today. So again, like the plants that went extinct, these guys are more seasonal warm climate rather than hot dry climate plants. And then finally, let's look at the ones that were locally extirpated, the ones that disappeared but then came back again. We've got dawn redwood, ginkgo, a couple of kinds of sycamores, something in the birch family here, and something in the oak family here. So again, these sort of warm but relatively seasonal climates where there's some fluctuation today, that's where their living relatives are. So what would explain this kind of shift in the composition of the flora? Well, I think what's going on is that we have a mid-latitude site. So here's the Bighorn Basin. Now we're looking down on the North Pole. Notice there's no ice cap there. This is an Eocene reconstruction. Also notice that there's a little more connectivity among the northern continents because the North Atlantic isn't so big, and there seems to be land over here in Beringia as well. So what happens, I think, is basically that as the PETM comes on, there are plants that were living much farther south. They move up through the Bighorn Basin area, and actually during the height of the PETM, I think that they're actually exchanging across all of the northern continents. So they're able to move, they're able to grow and disperse, starting in North America, getting to Europe, and also to Asia. And basically they can go all the way around the pole between the northern continents. Then as the event wanes and it starts to cool again, basically they all scurry back to the south. There are populations of those really warm climate plants that were up here are going extinct in the northern parts of their ranges, and they're persisting in the southern parts of their ranges. So, and also some of the species that were able to get around between these northern continents during the warmest time are showing up here in the Bighorn Basin where we're sampling, but they hadn't been in North America before because they're coming from Asia or Europe. So basically, to summarize, we have at the beginning of the PETM, at the onset of the event, a local or regional extirpation of lots of these temperate deciduous plants, things like dawn redwood, birch, sycamore, katsura tree, and simultaneous with their local extirpation, there's this immigration of dry tropical plants, of the beans and other things that go with them, into northern Wyoming. That kind of flora persists in northern Wyoming for 100,000 years, 120,000 years, something like that, and then it begins to shift back again. So during the recovery, you get the local or regional extirpation of those populations of the dry tropical guys that had gotten that far north, and you get the return of the natives, plus some of these intercontinental migrants that came from other continents across the high latitude land bridges during the warmest part of the event. And coincident with that, there is some extinction, but it's not a huge extinction. This is not a mass extinction. It's maybe 10%. And just to give you a sense of what that might have looked like, this is an artist's reconstruction of the latest part of the Paleocene with nice ginkgo trees here and alligator-type things living in the water, and dawn redwoods and other conifers growing off in the wet places. And then during the PETM, it would have looked more like a dry tropical forest. And then at the end of the event, you're back to a wet forest, something like the one that you started with. So what else happened? We talked about the plants, but it turns out that this event has effects that go up the trophic chain. So it's not just about the plants, it's also about the insects. And with some colleagues, I've done work on insects eating plants. So this is actually one of the most amazing kinds of fossils you'll ever see. And you can see these things that look like little paper cutouts. And those are fossilized insect bite marks on fossil leaves. And we know that the insects ate the leaf while the leaf was on the tree, because that brown rim there is basically the plant's version of a scab or a scar. It's the reaction to being eaten, and it seals the leaf off. So that wouldn't have happened if the leaf had fallen first and then been eaten by an insect. This is recording an interaction between an herbivorous insect and a kind of plant. And what we found when we looked at the leaf fossils from the PETM was that they had much, much more damage than the leaf fossils from before or after, and also more kinds of damage. So it appears that insect herbivores became more active and also more diverse during the event. And that's actually consistent with predictions from greenhouse studies, which show that if you put plants in a high CO2 atmosphere, they tend to make less protein, and the insects that eat them have to eat more plant matter in order to get the same amount of protein. So this is a really interesting observation. There are also changes going on even higher on the food chain. There, among the mammals, this PETM event is associated exactly with the first appearance of the relatives of horses and the first members of the order that includes sheep and goats and pigs, and the first members of our own order, the primates. This is when all of those groups show up in North America. So we think they're also coming probably from Asia or perhaps Europe, but certainly they're not in North America before the event. So these look as if they're migrating. And something else that goes on in the fauna, we get a very sudden change in body size. So this is a complicated looking graph, but basically time is just going up. It goes from lower to higher. This is the onset of the PETM here, this red line. And this green line is showing you body size of these little horse-like critters that showed up just at the onset of the PETM. So they appear, and the first thing that happens is their body size decreases by about a third. And it stays small for maybe 80,000, 90,000 years, and then it increases again. And that size decrease is more or less exactly coincident with this really warm period during the PETM. If you look at mammals today, they often have smaller body size in warmer climates. So it may well be that these little horses are evolving to smaller body sizes in response to the hot climate, and then evolving larger body sizes again as the event goes away and it cools down. So what are the lessons from the PETM? There are basically 4 of them. First of all, this big release of carbon. If someone says, well, I don't think carbon dioxide really would change climate very much, you can say it's happened before, and when you release a lot of carbon into the atmosphere and the ocean system, you do indeed see a warming of global climate, and you see dissolving of these deep marine chalk deposits. Basically, the ocean has a lower pH, and it results in dissolution of carbonate. Secondly, we think that there's, and this is sort of at the edge of what people are doing right now in terms of new research, but we think that there are probably self-reinforcing cycles here in the carbon, the way carbon behaves. That, in other words, the carbon is released, perhaps it's initially triggered by volcanism in the North Atlantic, and magma heats up rocks or sediments that are full of carbon, and that drives CO2 and or methane into the atmosphere. But once the atmosphere starts to warm, it causes the ocean to warm, and it also shifts the rainfall patterns on continents. On continents, this may result in more wildfires, which would result in more CO2 going into the atmosphere. In the ocean, it warms the surface ocean, which warms the deep ocean, which warms those methane hydrate deposits, and that puts methane into the atmosphere, which causes more warming. So we have the potential here for self-reinforcing cycles that are really important for us to understand in the context of today. Third, we have pretty good evidence here that once you get the warming going, it doesn't go away very fast. So the effects of this warming event, the onset is relatively rapid, but it lasts for a couple 100,000 years. So once you get the carbon into the atmosphere, it takes a long time for it to come out. And then fourth, this rapid global warming, it changed a lot of things. It had a huge effect on the ecology of terrestrial systems. It changed where plants and animals lived. It changed how they interacted with one another, and it even drove rapid evolution in some kinds of animals. So carbon's really important. Carbon's really important based on this historical example. And I'm just going to very quickly mention this isn't the only one. So the PETM is one of the best understood carbon outbursts in geologic history, but it's far from the only one. And I'm just going to mention there's one that happens more like 200 million years ago, right at the end of the Triassic, beginning of the Jurassic. There shifts in carbon isotope composition. Again, this is something that happens at the PETM. And here it's associated with a much bigger extinction and also with an outpouring of flood basalts. These are the Palisades on the Hudson. Those basalts date almost exactly to the initial opening of the North Atlantic, and the disturbance to the biota and the extinction that's associated is probably, at least in part, a consequence of climate change that relates to CO2 that was released during that phase of rifting. So carbon is turning out to be, over and over again, as we get a better understanding of the history of climate and the history of the biota on this planet, it's turning out to be really important. And that's why I think we need to be thinking about it harder now. So I don't know how many of you have heard the word Anthropocene, but the idea is that this is a new phase in the history of the planet, and it's called the Anthropocene because we, humans, are starting to have a geological sized impact on climate, on many, many aspects of the Earth system. And this shows up very, very obviously in graphs like this one. Here's the number of billions of tons of carbon that go into the atmosphere from fossil fuels and cement production every year back to 1750. So, you know, we're now putting in something like 10 billion tons every year. And you can see that it's climbed very sharply. And a lot of people have seen graphs like this, but you less often see graphs like this one, which is the cumulative carbon emission. So this is the same time period. Here's the blue line from the last graph. This is what happens when you actually just add it up, right? So this is how many, now instead of going from 0 to 10 or whatever, this is going from 0 to 400 billion tons. Remember, does anybody remember how big the PETM was supposed to be? It was like 5,000 something billion tons. This is, so we're still far short of a PETM size event, but we've put something like 360 billion tons in since the beginning of the Industrial Revolution. And you might wonder, well, what difference does it make that the cumulative amount? The reason that's important is because a lot of that's still in the atmosphere. CO2 doesn't come out of the atmosphere that fast. So of the amount that we've put in, there's still something like 250 billion tons residing in the atmosphere. That's why CO2 has gone up. And it takes a long time for it to come out. So here are some model runs that are completely consistent with what we know from the PETN that show that there's a stipulated 5,000 billion ton release at the beginning of this model run, and then time here is going out to 10,000 years. This is the initial amount of CO2 in the atmosphere, and you can see that even 10,000 years after this release, 15 to 40% of the carbon is still in the atmosphere. Weathering, these are processes like weathering are really slow. They don't take up CO2 very quickly. So there's a huge hangover effect of putting CO2 into the atmosphere. And of course, as CO2 stays high, temperature also stays high. So this is another model simulation making some assumptions about how much CO2 might be released, 7 billion tons a year here, so less than the last few years, increasing at 2% per year and just burning up all the fossil fuels, so a total pulse of 5,000 billion tons. And here you can see it goes out to 3,000 in the Common Era, and temperatures are still just as high as they were at the end of the carbon release. So because the CO2 stays in the atmosphere, it stays warm. And if it stays warm for a long time, a lot of other things are going to change. So this is a map of where I work with 10 feet more of sea level, which is, you know, IPCC projection for 2100 is 1.5 to 3.5 feet. This is a very uncertain figure. People are having a hard time figuring out exactly how large ice sheets will respond to prolonged warming. But it's not inconceivable that sea level could be this high by 2200, and that would make people's commute to work more difficult. This is what sea level would look like if we lost the Greenland ice cap, which is a conceivable thing in 5,000. The most amazing thing about this is that there's still a traffic jam on the 14th Street Bridge. I'm tempted to boast that Washington is reputed now to have worse traffic than LA in many parts of the year. So I know fighting words, but yeah, it's bad, but it would be worse with this. And that water is likely to be much more acidic. So again, this is a projection for possible tracks of ocean acidification given different scenarios of carbon release. So I've talked a lot about carbon. There are lots of things that make the Anthropocene a very intriguing idea. There's new topography that's being created in many parts of the world. This is a coal mine, a mountaintop removal in West Virginia. We're changing the nitrogen cycle. So nitrogen is an essential nutrient for plants and animals, and we are now at a point where most of the nitrogen that's fixed, so the nitrogen, there's lots of nitrogen in the atmosphere, but it's chemically pretty or biologically pretty inert. You need nitrogen in a biologically active form. That's generated by some kinds of microbes, but now most of the biologically active nitrogen is created by people. We use natural gas and power to manufacture chemical fertilizer, and so our own existence, like probably 50% of the nitrogen atoms in your body were made by people. I mean, they were pulled out of the atmosphere by people and turned into reactive nitrogen by people, fed to crops, fed to animals, and now they're part of you. So this is a really profound change, and it's allowed us to create a very different kind of distribution of biomass. This is, I don't know how many people here see XKCD. It's a web cartoon. It really has a lot of amusing things on it. But here, it's the drawer of that has just symbolized the distribution of biomass among different kinds of land mammals. And you can see that, here we are in the middle, and here are the critters that we either eat or take care of in the light lavender color, and then all of the wild vertebrates are 3% of terrestrial biomass. We're also modifying a lot of biomes. The take home here is, if you're interested in wilderness, 23% of the planet is now estimated to be relatively wild. The rest of it is pretty heavily human modified. And finally, globalization. We're doing a pretty good job of mixing faunas and floras from different places. There are a lot of parts of the world now where something like 20 to 50% of the species of plants come from somewhere else. So these are the sorts of things that will show up in our fossil record, the fossil record that we're making, and that's why people are talking about the Anthropocene. But I want to make a slightly bolder claim, which is that the Anthropocene actually can help us maybe see the future better, in a better way. And I think this is kind of where the state of the discussion has gotten to be on a lot of environmental issues. And I don't know how well you can see the cartoon, but this is supposed to be Al Gore. This is the conservative cartoon. Here's Al Gore in religious robes exhorting his eco-freaks to take care of the planet, or whatever the message is there. But I think that the message behind that by the person who drew this, I think, is that environmentalists are people who value nature more than people. And in the other corner, we have this cartoon showing the big business magnate who's talking to people and telling them not to worry as sea level is rising out the window, and he's the one with the life preserver. And the message there is that business values money more than people. So I think both sides are accusing the other of valuing something more than people. And what I'm hoping is that the Anthropocene perspective is something that can help people get over that. So what the geological perspective says is that the Earth has always changed, that we've always changed, that there was never a stable state of nature. So if you're thinking you need to go back to the way it was, that can't happen, and it never has happened. So that's something that we may have to sort of give up on. There's no purity in the way it was. We're part of it. But I think it's also important to look back and to think that talking about what happened in the past is a way of saying these are processes that just work. They're not, it wasn't, the PETM was nobody's fault. This is a blame-free zone. It happened millions of years ago. And we can talk about the severity and the rate and the scale of the changes that we're causing without being apocalyptic. We can say, well, we're probably going to cause a lot of extinction, but we're not going to kill ourselves off, probably. We're pretty resilient. We have a lot of technology. We might cause suffering to a few billion people. That's a really terrible thing, but I think it's important not to be hysterical about it, if we can try to do that. And it's also, I think, important to realize that we need to manage the planet. I mean, that's what we're doing anyway. We're doing it largely unintentionally, and we need to do it better. We need to do it knowing what the rules are, and we need to know what the rules of the planet are. We also need to know what the rules of ourselves are. So let me finish by saying that like 2 months ago, a friend called me up and said, there's this new book out. It's called The Sixth Extinction. And in The Sixth Extinction, Elizabeth Colbert says, we're like the asteroid that nailed the dinosaurs. And she said, what do you think of that analogy? I mean, you're a paleontologist. What do you think of that? And my first reaction was kind of nerdy academic reaction was, well, let me see, the KPG extinction, that was, more than north of 50% of the species, and we've only taken out maybe, less than 5% so far, we think. So it's not a good analogy because the number's wrong. And then I kind of got hold of myself and realized I was nerdy. And I thought about it more, and I thought, on the surface, that it kind of works, because we are causing extinction directly and indirectly. And we're changing the climate, we're changing nutrient cycles, we're changing the chemistry of the ocean and nearly everything else. So we are affecting the history of the planet in really significant ways. But when I look past the surface of the metaphor, I see something that I really don't like, because it implies that we have no knowledge and no volition and no capacity to change our course. And the idea that human actions are as inevitable as an asteroid impact is really depressing to me, and I think also fundamentally wrong, because we know we can do really big things intentionally as well as unintentionally. So I'm going to offer my improved metaphor by saying that I want you to imagine that that asteroid 66 million years ago, and think about it from the asteroid's point of view. So there you are, a mountain-sized rock sailing along through space, and you get whacked by a planet that's 1 billion times your size. Adding insult to obliteration, the planet is dirty and wet and covered with organisms. Ew. Your last act as the asteroid is to make a few adjustments to the biota, wiping out dinosaurs and leaving an opening for small, furry vermin. And now here we are, 66 million years later. The planet continues in its orbit, and the descendants of those furry vermin are sitting here in this room with me, and we're coming to some kind of consciousness. What we're becoming conscious of is that we have a huge sway on this planet. In a sense, we occupy a control room, a bridge, and the full meanings of all the dials and the gauges in that control room are just starting to become clear to us. we need to apply a knowledge that we haven't really fully established yet. We're still working on that. But we can read the logbook of the planet. That's what I've been talking about. And we can see where we've been, and we can use that information to influence where we're headed. So we can make things turn out for better or for worse, at least from our own perspective, and possibly in some sense from the planet's perspective. Life has a 3.5 billion year history on this planet, and there's never been a purpose to that history. But there could be if we decided to give it one. So, thank you.
So we will take some questions, and how this will work is there are ushers who have mics, and so if you have a question, raise your hand, and one of these guys will come bring you a mic, and we'll use the mic. So if you have questions, go ahead and you can start over here.
Hi, thanks for a great talk. I just wondered if you might enlighten some people in the audience about what happens to the carbon. So how does it get removed once you've made a big spike?
There are several processes that remove it. I mean, the first thing that most of us think of is photosynthesis. What happens with photosynthesis is it works pretty quickly, but it usually doesn't result in the carbon being kept out of the atmosphere. So most of the organic matter that plants make gets recycled back into the atmosphere. So a lot of it ends up in the ocean, in the surface ocean first, and that happens relatively quickly over decades or years, and then eventually gets mixed deeper into the ocean. So that happens over hundreds or thousands of years, and then eventually it's removed by weathering, which results in soluble carbon-containing compounds that end up in the ocean. And so there are different routes for carbon to leave the atmosphere. Some of them result in basically the carbon going right back up again. Others are slower but result in a permanent removal or much longer term removal. Eventually it does end up back in the atmosphere because it gets subducted on a plate and shot back out of a volcano, but that's really long term.
Yeah, I was wondering how you date the plants and stuff that you're doing for one thing, and how sure are you of the speciation?
Okay, so the two questions. One is how do we establish the age of the fossils that we're looking at, and the other is about speciation. How do we know what species we're dealing with? So the absolute age of many of the fossils is more difficult to know than the relative age. So relative age we can do lots of different ways. We can just walk up the side of a hill, and we know that the older rocks are at the bottom and the younger rocks are at the top. That change in carbon chemistry, the stable isotope shift, is something that is so large that it's highly distinctive, and we can actually trace that in different places around the world and know that we're looking at exactly the same time whenever we find that shift. And that's the most common way when you're working right around this event. You're often using, you're searching for that carbon change. Then in almost every setting you have some other ways of getting at the age. Either there's a rock that you can date radiometrically, or there are changes in the Earth's magnetic polarity that you can use. So there are other ways that you can get at it. In terms of the species, what we are working with mostly are leaf fossils, and they're really intricate, and they have a lot of detail in the venation. So what we do is essentially study the fossils really carefully and try to characterize them quite precisely, compare them to one another, make sure that we're dealing with different types. Sometimes we don't know what kind of plant they are, we just know that they're different from all the other ones.
Could you talk a little bit about methane hydrates?
Okay, so just to say something about methane hydrates. I am not a methane hydrate expert. I let you know at the beginning. But essentially, so where they come from, they're microbes that live at the bottom of the ocean. They essentially are eating organic matter that falls there, and they produce methane. Methane is semi-stable at the temperature and pressure at that far down, so it creates these hydrate compounds. With regard to the PETM, there's some uncertainty about exactly the volume of the methane hydrate reservoirs that far back, because we don't have any direct way to assess it. But we do know from looking at them today that if the temperature increases or the pressure decreases, that they can destabilize. So they also have a very characteristic chemical composition in that the carbon in them is there's much more carbon-12 and much less carbon-13 than there is in most other reservoirs of carbon. So one reason we think that the PETM involves methane hydrates is because it's such a big shift in the carbon chemistry. And so we think that it was tapping into a reservoir of carbon that had a lot of carbon-12 in it.
What about the permafrost?
The permafrost also has the potential to release carbon if it's warmed up and not frozen anymore. And there's also methane trapped in that as well. So again, they're kind of complicated problems of trying to use the ratio of carbon-12 to carbon-13 and the amount of dissolution we see to constrain the possible reservoirs that were tapped into when the PETM happens. And they don't yield unique solutions. So we're still trying to find other ways of getting a bead on what reservoirs were tapped. And of course, if there's more than one reservoir tapped, then it gets even more complicated because you need to figure out, is it 10% this, 20% that, 30% something else? It starts to get really complicated, which is probably why it's been so hard to figure out.
Okay, well, I think I'll have, one more. Sorry, I didn't see your hand.
Just one quick question. You mentioned a book towards the end. It's called
The Sixth Extinction. It's by Elizabeth Colbert, Kolbert, and it's on my bedside, and I'm like 3 chapters into it. It's wonderful reporting. I'm cautious now in a way I never have been before about being too defeatist. I think that there's a real there's a problem with talking about everything that's going wrong or has gone wrong already, because I think a lot of people have become sort of deadened to the idea that, yeah, I mean, how often have you heard someone say, yeah, I guess we pretty well have screwed it up, or yeah, we're going to drive ourselves extinct, or some words to that, or we're ruining the planet. These are common phrases, right? And I think they're not scientifically accurate. They're kind of emotionally, you can get into your self-pity or something. But, I don't think it's justifiable to be that pessimistic. And I think it doesn't, politically it's not helpful to be that pessimistic. I think it's better to say, look, we've done some pretty amazing good things. I mean, you can cite chlorinated fluorocarbons, you can cite acid rain as fairly major shifts. And this is there are many more, and there always will be. So it's time to start, kind of thinking, it's not that there's not a lot of bad things happening, it's that we have to continue to work on solving them.
I think with that, just because of our hour, we'll thank Scott, and you can ask him afterwards. So anyway.